Thanks everyone for coming to PyData Global 2021. And thanks for coming to James Powell's live Q&A on be a Pandas expert. And I'll just go ahead and hand it off to James.
Thank you for that, Scott. Good morning, everybody, and welcome to a follow-up session to my PyData Global talk. I am, of course, James Powell. For those of you who haven't had a chance to meet me in person, I serve as the chair of the NumFocus Board of Directors and also the vice president of PyData. But beyond that, I also dabble a little bit in tools like NumPy, Pandas, broader Python technologies, and I've been to a lot of these events and given quite a few talks. The question of how to be a Pandas expert can either be answered in 1 minute, maybe less, maybe 15 seconds in one sentence, which is learn how indexing and index alignment works, or in 2.5 to 3 hours by really understanding what I mean by indexing and indexing alignment. And so I apologize that when I was faced with the dilemma of whether I give a 1-minute talk, which is just me saying the word index over and over and over for 1 minute, or whether I give a 2.5-hour talk, which is me saying the word index over and over and over and over with some live coding behind it, I opted for the latter, which is why we pre-recorded the tutorial just to give you an opportunity to absorb all of that material. Now, I don't anticipate that all of you, or even that many of you, probably had a chance to watch that, but what we can do in this session, if you don't have specific questions, is I've prepared another maybe 2, 3, 4 hours worth of examples, of which we'll try and cover as many of them as we can, that touch upon all of the ideas that are covered in that tutorial. And so you can see these in practice, and then maybe if there's something interesting there or some ideas that you find might be worth following up on, you might go back to the video and take a chance to look at it. But before we jump into any of that, I do want to see from the audience, I want to open up for any Q&A and see if there are any specific questions that arose during the talk. And there is one question about what the tea that I'm sipping. It's the same tea that I drink every morning. I have some tea that I got from the UK, some nice Earl Grey tea in the morning. For an afternoon talk, I would be drinking maybe a nice green tea or something like that. But having answered that one question about our tea, I want to open up for any other questions, maybe related to pandas, indexing, NumPy, Xarray. I think the talk ended up touching upon quite a few things. And towards the end, I basically went through about 80% of all the methods you have on a pandas data frame and showed how every single one of them can be, maybe is not something that directly operates on the index, but is something that's either index aligned or something that has some consequential aspect of it related to the index. It's just probably the most dominating and most interesting thing about pandas. But it doesn't seem like we have that many questions. Oh, do the concepts of index alignment apply to Dask as well? This is much harder to say. I think the Dask data frame is an attempt to mimic the API of pandas in order to present a computationally similar environment with different execution. But one of the things about the index is the index, if it's a mechanism, is fairly difficult for you to serialize, and it's a fairly difficult thing for you to distribute without a lot of additional mechanism behind it. And so while I'm not a Dask expert, although it's one of my goals for next year to become a Dask expert, I suspect that there are some significant distinctions between how Dask handles the index and the pandas. I wish I could answer that a little bit more authoritatively, but that's about the best I can do for you for now. In the pivot table operation in pandas, what's the difference between the index and the group by parameter? The index parameter is going to set what the index is, and the group by parameter is going to, oh, that's interesting. These are small details. My gut feeling would be that when you look at a pivot table operation, it's basically equivalent to a group by unstack. And so I suspect, I don't know, we'll have to look at the API. We'll have to look at the API to answer that. So let's jump into the other material that I have, and let's take a look at the documentation and see if we can answer that question. And so in just a moment, I'll share my screen with you. Behind me, you'll see my screen. I'll hide in the corner here, and you can see I have a little bit of follow-up material. I want to answer this question about the group by parameter. Part of what the point I wanted to make regarding being a pandas expert is, it is generally not the case that expertise of these tools requires memorizing the API and knowing all the names of the keyword arguments, knowing all the different modes that you have. because these things change, and they change very quickly, and they change over time, and nobody can keep up. And as a consequence, what I think you need to do if you want to develop expertise is understand the core ideas, the core concepts. And once you have an understanding of those core ideas and those core concepts, then most of the time you can look at something that you haven't seen before in the API, and you can kind of make sense of it, building upon a framework that you have. And so as an example, if we were to go to pandas.pydata.org and look at our operation for pivot table, we'll see there's apparently a group by argument here. Is there? Oh, I see. It's not a group by keyword argument that you're asking about. It's the group by operation in the pivot table. Oh, well, the difference here is the group by operation is going to preserve the same column index. And so it's just going to operate on groups defined by the row index, whereas a pivot table can both change the row index and the column index. And so you can see here, I don't have an exhaustive understanding of, or an exhaustive knowledge of all the different keyword arguments on these different methods that you have in pandas. And so it threw me a little bit, what would the group by mean? Because presumably, that would be handled by that index parameter. But I think the question instead was actually, what is the difference between these two different operations? And largely they do something very similar. It's just that in the case of the group by operation, you keep the same columns. But with that said, let me show you one or two very quick examples. I'll live code these for you for cases where you might have an intuition to use pure Python, or you might have an intuition to use NumPy, but this idea of index alignment can be used effectively to answer real questions in a terser, less mechanical, more direct fashion. The first is an example pulled from some data sets or some synthetic data sets for modeling a problem that I was working on, which was you have a series of actions that are performed on some entities. And you need to make sure that those actions performed on those entities are consistent. And most of it is moving things in and out of some sort of till or some sort of book. So the idea would be that you have, a bunch of data sources, like 5 files that correspond to this information on 5 distinct entities. And for each of these entities, if you look at one of these files, it's just a sequence of, just as a simulation of the idea, this is just a sequence of numerical values that have moved. And so this is just taking that same general idea and saying, this is like a till, and you're moving money in and out of this till, like 25 cents is a quarter, 5 would be a $5 bill, 1 would be a $1 bill. And what you want to make sure is that at every point in time, this till is consistent. If you had 5 $1 bills or 5 €1 notes, you couldn't at some later point give away 6 of those, because then you'd go negative. And so it's trying to figure out, how do we make these things consistent? And when you look at this data, the data itself is actually relatively easy to parse and to load. This is basically NumPy load text data. And so nothing really stops us from saying, you know what? These are just our transactions loaded from this file, and taking a look at these transactions and saying, you know what, NumPy and DRA, I'm done, I don't need anything more. And then maybe I'll do some sort of looping over this NumPy and DRA, or maybe some sort of operations on this NumPy and DRA. But what you can see is what Pandas adds on top of your simple NumPy-like structures, your simple, one-dimensional structures, is the ability to add the index being some sort of metadata that has well-defined semantics in terms of data operations, and that then allows you to perform human meaningful operations on this data. And so what I would do instead of solving a problem like this in pure NumPy, where I'm trying to say, okay, if you got a $100 bill at the beginning of the day, and then you got 2 $20 bills, and then you gave away 3 $20 bills and a $100 bill, you should end up with negative 1 $20 bills, that's inconsistent, and no $100 bills. I'm trying to track those things. And if you think about it, this is a fairly straightforward problem to solve in Pandas. We'd start by modeling these transactions as a series. And this is the case where we can immediately talk about how this data may look like, or rather when we use Pandas, it may look like the index is something that we care about when we're talking about and let's just comment this out because I don't need to sprint to the screen. It may look like it's just the row index And I often complain about these things here that you see, these range indices, but this range index is actually correct for this data. This range index corresponds to this numbering from 0 to 300 corresponds to the number of the transaction that we happen to be looking at some point in time. So the 0th transaction, the 1st transaction, the 2nd transaction, the 3rd transaction, and so forth and so on. So for the indexing that we want to do, it is not on the rows. The indexing that we want to do is actually going to be on the columns. In fact, what we probably want to do with this data is we want to pivot it. And if you think about these operations that you can perform on a Pandas data frame, like melt and pivot and stack and unstack, largely they are operations that are about moving either things from the data portion into the column index, into the row index, from the row index into the column index, or vice versa. And so a pivot operation, very straightforward. It's a dual of the melt operation, where the melt operation moves something from the column index down into the data portion. A pivot can move something from the data portion up into the column index. And so if I were to do this, what I would probably want to do is set my index, actually set my columns to this one transaction operation. So let's do this. And let's actually, let me do this a little bit differently just to make this easier with the pivot. Because I can't pivot on a series, and series doesn't have any columns, but I can pivot on data frame here. And I can make this a data frame carrying 2 pieces of information that I want, where the first piece of information is the actual transaction. And the second piece of information is the denomination. Right? And this will just be the absolute value of the transactions. And once I have that, then the way to solve a problem like this is fairly straightforward because, oops, this is, let's just do apps like this. There we go. And if we can manage to spell everything correctly this morning, what I want to do is I want to take these values in the denomination column and I want to pivot them up into the column index. So here, denomination, like that. And here you can see now what I've created is a data frame that represents, oh, you got a $100 bill, $100 bill, $100 bill, and it's now pivoted these operations correctly. And then what I can do from here is fill in a bunch of zeros for every time where nothing happened. I can take this result and I can divide it by the value of its columns. So this gives me basically a 1 or a -1. Oops. So that's good, that's good. And let's double check one thing here. Okay, very good. And so here I want to take, I have the transaction denomination. Oops, I wanted this to be the other. Yeah, that's correct. That's the transaction number, that's the denomination. Yes, that should be very good. So I should be able to divide this thing by its columns. And let's take a look at what the columns actually are. And so there we go. Oh yeah, and I want to, okay. And so here I also want to do, let me set the index here. Let me set the, I think I want to set the values here and set the values to what the transaction is. There we go. And so here you can see this is actually what I wanted. I wanted the values of these things to be the transaction. There we go. And then I can pipe this and divide this by its columns values. And so now I get 0, 1, or -1 values, depending on whether, this thing changed hands or not, whether this thing, whether you got one of these or didn't get one of these. I can turn these all into integer values. And then, the answer for whether this is consistent is do a cumulative sum or expanding sum, and then it'll sum things up. And so you can see at the end of this day, you had 80 of these, 89 of these, 26 of these, and 20 of these. To see if this is ever inconsistent, you look for anything where this is less than 0. So you do something like less than 0 and then do, any on this to see if, you ever gave away more than you had, and so forth and so on. And I'm doing this on just one data set. If you want to do this on all the data sets, what you do is you do this exact same operation, except this part here would be the inner level of a multi-index, and the outer level of that multi-index would be the actual entity that you're looking at, and you do this within a group by operation. So you just set this up and then do a group by and then another rolling operation within it. And this is a very common pattern that you see. In one of the later examples, I can show you how you can do group bys with expanding and rollings within them. And so one question about when you use pandas and when you use Spark, it's a very good question. And in the case of pandas versus Spark, I think the major difference is, does your data fit into memory? And does your data have complex indexing? One of the nice things about the pandas index is because it is written in pure Python code, and it's a pure Python mechanism, it's possible that you can write very complex mechanical indices that really only are well defined in terms of Python code that you have in front of them. And so I would say that in terms of pandas versus Spark, the core reason for pandas would be, well, if I can fit everything into memory at once, it's fine. And if it's the case that I have some very complex index, like an interval index or whatnot, I don't know if you can do the similar in Spark. Now, I want to push on to the next example, which is a little bit harder than the previous example, but maybe a little bit more interesting. This is an example that I needed to do, or this is actually an analysis I needed to do fairly recently, which was I was going online and I was looking at hard drive prices because generate a lot of video content. And when you generate a lot of video content, you generate a lot of files. And because there's a lot of data, you need to store it somehow. And so the question was, well, which hard drive should I buy of all of these choices that I found online? And the problem with this question is, naively, what you might say is, what's the price per gigabyte or the price per terabyte? And so here you can see this is clearly some sort of CSV-like data or tab-separated data with the manufacturer, the size of the drive, and its cost. And you might say, I'll just divide the size of the drive by its cost or vice versa and optimize for that. But when you do that, you're actually going to find that the stuff that they don't want to sell anymore, they don't want to keep in inventory anymore, is very cheap. And it's the stuff that you don't really want to buy. Because if you buy a 4 terabyte drive, great, you're just going to have to buy another one in 2 days' time or another one in 3 days' time. And so it's actually not the best purchase to make, because from an operational perspective, you're just going to be stacking up, your power requirements and your requirements for containers for these drives. Instead, what you might want to do is you might want to perform an analysis that looks like this. Given the average prices per drive, how much loss is there if I purchase any of the other ones at their actual price? And so, for example, if I can buy something for $1 a terabyte, and then I purchase something that's 12 terabytes for $1.50 a terabyte, how much do I actually lose? And I actually lose $6 there. And so is that survivable? And so what you'd probably want to do is set a threshold and say, I'm willing to overpay up to say $50 or $80 if it means I can buy less physical hardware. And so it's a little bit more complex of analysis, and it's a very easy analysis to do in Pandas. And so what we'll do is we'll take this raw data, we'll read this in using read CSV. And so we'll do a read CSV of our data. The separator for this data is just the regular expression separator, any number of sequential spaces. And let's do this, and let's print this out as we go. And there's no header on this. And what else do we have? Let's title the columns. That'll make our life easier. And what are the columns? The columns are the manufacturer, the size, and the price. And, if we're here to talk about the index, then we better set an index on this thing. So what we'll do is we'll set the index, and the very reasonable thing, the way I'm going to look up this data, the way I'm going to categorize this data is by manufacturer and size. And we'll sort it on the index. It's not a bad idea to just sort on the index, because any group by operation will be able to see the index is sorted. Pandas indices know that they are in sorted order. They know they're monotonic. And so group by operations don't have to do redundant sortings if they're performed on the index and the index is already sorted. So if I'm doing a bunch of work on this data frame, that might be useful. So I get something that looks like this. This is not actually actually we'll keep this as a data frame, although I could squeeze this into I could squeeze this into a single series, but I'll leave it as a data frame for now. What I can think about is here for my analysis, I can actually unstack, by stack and unstack operations, give me the ability to take things that are in this row index and put it into the column index. So an unstack on the manufacturer just pulls that level up like that. But what I actually want to do here is I want to do something akin to like a Cartesian product. What I want to do is I want to take every price against every price, or I want to take every relative price against every relative price, map them out. So I want to say, what's the price for the 4 terabyte item given or what's the price for the 12 terabyte item given the unit pricing of the 4 terabyte item? And this ends up being fairly straightforward to do. What I'll do is I'll take a mesh grid of the prices divided by their index. You can see because the indexing here is set up the way it is, and let's do one thing. We're going to get mesh grid from NumPy. And here, just for the purposes of our analysis, let's just look at one manufacturer, and then we can generalize this to all of them. But usually that just means some sort of group by operation. And so just to keep our lives easier, we'll do this, and we'll actually squeeze this into a series, or we could have done, a squeeze equals true here if we wanted to. But here you can see if we perform, and let's do this. And let's also get what we want, mesh grid here. There we go. Here you can see we have the original prices. If we divide them by their own index, then we get the per unit pricing. If we take that and we do a mesh grid on it, we get all the ways you can repeat this. We get the tiling and the repeating of this thing. And if we mesh grid it with its own index, then what we get is all the ways that you can repeat one of these against the other and the other one against the first. And so we get the ability to say, okay, this is the per unit pricing of one of them against the 4, against the 4, against the 4, against the 4, the 6, the 8, the 10, the 12, and the 14. What's the per unit pricing of the other one against all of these? And so mesh grid is just, this idea of tiling one and repeating the other, so you can do everything against everything else comparisons. And this shows up in the talk when I show you, if you wanted to compare every single value in a NumPy and D array against every other value in a NumPy and D array, that would just be an EQ on the mesh grid of the ND array against itself. And so here, this is a fairly common thing that comes up anytime you want to say, can compare everything in this structure against every other thing in this structure, perform that Cartesian product. And so what I'm going to do is I'll just multiply these, just pass these as 2 arguments to NumPy to multiply them. And there we go. And one unfortunate thing is this is going to give me this structure in the wrong order. I kind of want to say, given that you purchased this thing, give me this thing. The mesh grid is going to be transposed. Or the multiply is going to result in this being transposed. And so here we go. I'm going to put this back into a data frame. One of the things that I find can really indicate that you've gotten very comfortable with pandas is when you know exactly when you want to drop down into NumPy. And when you want to do the operations at the pure NumPy level and when you want to do them at the pure pandas level. And it's not just, I can't figure out how to do this here. I'll just get the dot values and figure out how to do it there, but it's quite judicious. And this is a case where you definitely would want to do this because there's no equivalent of pandas mesh grid because that's not really an index related operation. Multiply, this is just so that I can save myself, having to assign these to 2 variable names. And so here, it really is the mesh grid that kind of forces me to do the numeric operation on the raw numerical data in NumPy, or at least in the NumPy API, I should say, and then pull it back into the Pandas API. But what you can see here is, this is the original 4 terabyte at the 4 terabyte unit price. This is the 6 terabyte at the 4 terabyte unit price. This is the 8 terabyte at the 4 terabyte unit price, and so on. So if I take that result and I subtract it from the actual prices, I'll get the overage that I'm paying. But if I have a data frame, I always want to set up the index and the columns correctly. And so here, I'll just grab whatever the original index was here. And because I want to do this as a Cartesian product, both the index and the columns were whatever the original pricing was. And so let's do this. And so here you can see it very clearly. What we have is, if I purchased the 4 terabyte at the 10 terabyte unit price, if I purchased the 12 terabyte at the 10 terabyte unit price, is what we get. And if we subtract from this the actual original prices, then we get how much we're being ripped off. And so you can see, if you bought the 18 terabyte at the 18 terabyte unit price, you're not being ripped off at all because you're buying the same thing at its own unit price. But what you can do is you can look down these columns and say, you know what? If I take a look at this data, and let's round this data because it makes our life a lot easier to look at this. I don't really care about how many cents I've lost. If I take this and then I maximize or minimize down this axis, I can see what's the worst I could do. And so what I'll do is I'll minimize down the and I'll minimize removing the index. And so here you can see, this is the worst amount of money I could possibly lose comparatively based on what the cheapest actually is. And this is a much better analysis. And so in the end, I ended up buying the 18 terabyte drive because I thought $80, but I don't have to worry about this for a couple of months. Okay, maybe that's worth it. And so there you go. And you can see these are all a little bit of index operations and judicious knowledge of where Pandas really fits into my story. Now, let me take a look at any questions. And let me show you the next thing. The next thing is the star trader example. And the star trader example is an example of the power of index aligned operations and how you can use it to answer questions really, really easily in a very fluent fashion if you are aware of the index. And if you're not aware of the index, where things are just going to be, manual loops, extremely clumsy manual loops. And so Star Trader was a game from the 70s where you kind of travel between different locations and you sell different things to different people. It's one of those arbitrage games. You may have played one of these on a calculator back in the day. There's another one called Drug Wars, but here, this is Star Trader. This is the beginning of them. And so you can travel between these locations and you can sell these different items. And in order to model the Star Trader game, what I'm going to do is I'm going to model the market. And I'm going to model the market as a data frame. And the data frame is going to say at this particular location, the cost of such and such item is such and such. And so that'll model what all the different prices are. And then I'll model my own inventory and I'll see how to price my inventory against the market. And then I'll see how I might build a, strategy for analyzing where do I travel to in order to make the most profit? And then what do I purchase there and things like that. And so what I'm going to do is I'm going to generate this as random data. So here we'll use our default RNG. Like that. And what we'll do is we'll initialize this as something where the column names are each individual asset. And actually, I don't want to include the credits because the credits are your cash money. So what I'll do is I'll do this. I'll distinguish between the tradable assets and the assets that are not tradable. So here we go. So here we'll have each column be each one of these tradable assets, and each one of these will be a Pandas series with some random data. And the size of this is just going to be we'll pick two places where you can sell this thing. We'll pick between 2 and 1 more than half of the places where this can be sold. So I'm going to create a random set of numerical values, and I'll say, okay, maybe some particular item like metals or uranium or software can be traded anywhere from 2 to, say, however many total locations are divided by half. And so that means that not everything is saleable everywhere. And so that gives me that. And I'm going to, these are just random values. So let's multiply these times something larger and we'll round them as well. And I'm going to need this later. So let's capture this for a moment. And I'll index this series on however many stars that I want to pick, well, like this. And so here, what I'll end up with is I should end up with something that looks like, if I get all my imports right, I should end up with something that looks like this. And let's see, that should be nuts. Let's make this stars. Because you travel between the stars in this game. And let's see, there we go. And so here you can see at each location in the universe, this is what everything is worth, or this is what everything can be bought for. And the nan is meaningful here because it represents that you can't buy or sell that thing at that particular location. Let's round this to 2 decimal points just to make it easier to read. And let's just do something really simple here. Let's add in the untradable asset, the credits, and let's just set that to 1. And so that means that, $1 is worth $1 no matter where you go. So you can see $1 is worth $1 no matter where you go, but these different things have different prices in different locations, and some things are not tradable in some locations. Now, one thing that you find you do fairly often when you are really thinking about index alignment is you want to tell pandas how to perform the index alignment, especially on things that might be multi-indices. So you want to give your indices names. And this is how pandas will identify, oh, these are actually the same index. If there's a multi-index, these are the same levels. Let me do the alignment there. One unfortunate thing about pandas is the naming of one of these indices, it kind of prints in this ugly fashion. But I could have done the string here, but I actually like to use the raw Python object. Just to wrap this up, my inventory is actually fairly easy to simulate because here this is just a pandas series, would say anywhere from 10 to say 1,000 of each one of the tradable assets. And we'll just set the index on this thing to the tradable assets like that. And we'll just say, in addition to that, you start off your life with $100 as well, or maybe $1,000. And let's sort on this index here. And let's sort on this index here, might as well. And the biggest thing that would probably help us in our code is to learn to become a spelling expert, because it turns out that that is my greatest problem. Oh, and because I'm using these enums here, I have to, it's one unfortunate tiny thing I have to do. I have to do this. These things aren't sortable. So I'll do this. We'll make this an ordered enum. And you can see, the name of the game is to go as fast as we possibly can. Self.value less than other.value. And then the EQ is pretty much the same thing, except equivalent. And so this will allow us to do a couple of useful things like, grouping this thing if they're sorted. And let's make these ordered enums. So we can use some pure Python together with this. And, oh, we need to make these hashable too. There we go. So here we have the market, doesn't print out that nicely. And here we have our inventory. And the beautiful thing about this index alignment idea is, here's what I actually have at the beginning of the game. I have 1,000 credits, 270 star gems, 899 units of uranium. The total value of my inventory is the market times the inventory. And this isn't the total value of my inventory. This isn't the total value of my inventory at one location. This is the total value of my inventory simultaneously at every location in the galaxy at once. Let me remove the naming here because this is just, actually, I'll show you a little trick that you can do here. Here, this is going to be a little, actually, I'll just make this a string. It really sucks to do this value intermediation, but it's very difficult to remove that one part of it. But you can see here, this is the value of everything simultaneously in the universe at once. And so I could express this as a sum to figure out what the summed value of this is at every possible place in the universe simultaneously. Here, by default, it's summing, removing the row index and leaving just the ascending. So, the total, this should actually be mean for this to be meaningful. So the average value of my uranium is that, the average value of my metals is that, or I can do a sum on the removing the columns. And here is the total amount of money I have at all points. And so what you could think is, if I wanted to figure out how to do a strategy here, I would just do this and then say, what's the index max? What's the location I should go to? I would travel to that location. Ivan is where I can make the most money. I'd go to Ivan and then sell everything. And, I could compute what I'm able to sell pretty easily, because what I'm able to sell at Ivan is just the market at that location, dropping the nans. And so these are the prices, and these are the things I can sell. If I wanted to figure out what the actual items I want to sell, it's just the index of that. So these are the things that I can sell. And so if I wanted to, figure out what would happen if I moved there, I would just say, take this, divide it by that, and we'll drop the nans afterwards. And let's check one thing. Yeah. let's see what this gives us. Oh, the inventory is on, let's see what this gives us for a second. These should be index aligned, but there may be a, yeah, that's good. And our inventory is good. It's there. And so we should be able to do an index aligned division here. Just have to figure out why we get these obscure errors. And most of these times, these obscure errors are just some sort of index alignment issue. And so here in this case, it's probably just the case that I'm performing something. There's something in here that's coming out. Or what I can do is I can pull out those nans first. Let's see. If I multiply this, it gives me what the price of my inventory is. And so could just be my order denum. So we'll just fix this very slightly. This is a little bit too sophisticated with the order denum, but here we go. There we go. And so our index alignment should work. Again, the biggest problem in our life is really not the pandas index, is the spelling. And so you can see the index alignment actually worked the way we expected it to. There's just some small mechanics with this enum type. And what you can think is, this is how many of each of these things that I would sell. And what I probably do is I probably do a dot lock on this to remove the credits. And so what I probably do is I probably do a lock with the lambda, take the columns or take the index that this has, and do an index difference, removing assets credits. So I don't try and sell my money for the value of my money, which is meaningless. And by the way, this has to be a collection of some sort. And so here, these are all this is the number of each of the entities that I would sell, for some amount. And so I guess, sorry, this would be the amount of profit that I make by selling all of the particular items. And so here you can see this is the profit that I would make. And if I sum that, dropping the nans and whatnot, we get to what we want to get to. But the general idea here is by having these data frames and these series in this index aligned fashion, we can perform these operations just one simple line of code, just saying inventory times market value. Obviously, there's a little bit of mechanics if I'm doing something fancy where the actual index values are these enum types. Usually, you're dealing with things that are strings, and so everything's already built out for you. In this particular case, I had to make them sortable. I had to make them, comparable in some fashion. And you can think why that would be is because what's happening down the line is Pandas is trying to figure out how to match these up, so it's comparing them against each other. And that previous error was coming up because it's trying to compare one of these things against a none value at some point. Part of the calculation is trying to say, oh, wait, is this index, correct with this particular, or is this matching up with this thing? So I just have to make sure that these are comparable in a reasonable fashion. But if they are, then Pandas will do all of my index alignment for me. A much more sophisticated version of this problem is the trading example, the fourth example, where I go to the data that I shared with you in the talk. And we have some data corresponding to some trades that were done on some tickers at some point in time. And what we want to figure out is what is our position and what is the value of our position? What's the average buy price? What's the average sell price? How much of this do we have? And if we want to make this more sophisticated, we can even take into account that there may be some taxes or fees associated with these, and we can make use of some of the more sophisticated indexing mechanisms in Pandas, namely things like the interval index, to say if the trade was anywhere between 0 and 10,000 units, this is the tax that is applied to it. If the number of trades, I think for the fees, if you do between 0 and 5 trades a day, this is the fee that's associated. If you do over 15, this is the broker fee that's associated. So we could, in Pandas, not a whole lot of code, compute things like what is my position and what would my corresponding broker fees be? And these interval indices are beautiful because you can just say, oh, give me, I did 3 trades, what's the fee? And it will tell you fee is 0.15 because it's within this particular interval. And so you can see here that some of the other libraries that you might use that support a data frame like API, well, they're doing that in order to mimic what you're comfortable with from a analytical perspective, but it's fairly difficult to mimic the power of all of these arbitrary indices that you can use, in part because many of them are based on software mechanics that may not be distributable or may not be serializable in one fashion or another. I don't think in general a pandas index is serializable. It's just that the common ones happen to be. But it's really more of a mechanism for identifying how to go from a human description of the data to the physical description of the data, and how to line things up and match things up, and what is considered to be equivalent to what else. And in the previous example, I was using just a regular pandas index, just a regular object index, but I was using it with custom data. And you can see the trick there was to make sure that those enum types were correctly comparable to each other so that the index alignment would work. But for this example, we want to do something a little bit fancier. And so the starting point of this example would be, let's try and figure out what our position is. How much do we actually hold having done these trades? And so you can see for a particular ticker, FECI, we traded 13,500, and then we want to see not only what's our total holding, but when do we cross through the zero axis? So when does it go from a long position to a short position, and vice versa? To figure out the total holding, that's actually quite easy. With this, we just group by the ticker and then just sum, right? And so here, this gives you something that is indexed on whatever this group by operation is. And so here you can see for each one of our tickers, that's what our sum of, and we probably want to sum the volume because the price doesn't really make sense to sum. If we wanted to figure out what our average price was, we could take the mean of the price. That's fine. But part of what I want to show you in this example is one, look how lucky I am that I've generated random data with 4-letter tickers and nothing came up inappropriate. We're already on the right track. And two, I want to show you a little bit about the GroupBy API and how you can think about that GroupBy API via understanding of the index. Because there's like a GroupBy ag, a GroupBy apply, a GroupBy transform. There's all of these different operations that you can perform. What's the difference? Well, understand that the GroupBy ag and the GroupBy transform operate on a per column basis. They operate on one column at a time, or basically they operate on a one-dimensional structure at a time. In the talk, I make an argument for why pandas is really only one-dimensional data. A data frame is not two-dimensional. And I'll let you review why I'm so confident about that, or at least the argument that I make. But whatever the case is, if you're doing a group by down the rows or down the columns, you can only look at one of those entities at a time. You're only a one-dimensional structure at a time with apply, with ag and transform. With apply, all bets are off. You can do whatever you want. As a consequence, you can immediately see that certain things are not possible to compute directly with ag or transform, namely a weighted price. If you were to weight the price by a weighted average price, if you were to weight the price by the volume, you need two columns. You can't do that in a simple group by. You have to do a group by apply, or you have to do some sort of contortion, which gives you intermediate steps. And you may have heard people say that never apply is so slow. They're right, but they're usually right for the wrong reason. There are two applies that you have to watch out for in pandas. The first one is apply on a series object or on a data frame object. And this is where you operate some Python function, some Python user-defined function on the scope of every row of a pandas data frame, maybe every column of a pandas data frame. Actually, that's not really worth worrying about too much, but apply, if you're just doing it down the row axis, you're applying it on every single row, Python function every single row, or on a series on every value in that series. And the reason for that is your data frames are big. You've got thousands, tens of thousands, hundreds of thousands, millions of rows or more. Your series are very big. The whole reason you're using NumPy, Pandas, X-Ray, any of these tools is for this idea of a restricted computation domain. So you can leave the restrictions of the Python universe, dynamic dispatch, that things are all boxed, that you have arbitrary promotion of integers, things like that. And because Python function calls are very slow, it's about 7 C stack frames, at least historically, that's about what it's been to just invoke a Python function. They are currently working on making that faster, but just a Python function call all by itself is relatively slow. And if you're doing one function call per row of your data, and your data is structured so it's got a lot of rows because it's big data, then it's going to be slow. That's why you avoid dataframe.apply. That's why you avoid series.apply. But that's not why you avoid group by apply. Because what group by apply does is it breaks your data frame into groups based off of the grouping criteria, and then it applies the user-defined function on each group. usually it's going to be the case, a preponderance of the number of times, that the number of groups is significantly smaller than the total number of rows. Because if you had 10 million rows and you had 9 million groups, you're kind of be thinking, what is the group by really that useful for? Like, what is it really telling you? Usually it's like, oh, I have 100 million rows representing tick level data, and I've got 1,000 or 10,000 tickers. The group by apply is going to apply that UDF on the scope of the number of groups, which likely will be small enough that the penalty will be relatively low. It's not why you avoid group by apply. You avoid group by apply because then it's going to stitch these things back together. And it's going to do an indexed align concatenation. And anybody who's ever used the concat function in Pandas knows this is dog slow. Stitching these data frames back together, where you have to obey the index and you have to keep the index in its monotonic ordering, can be very, very slow. And if you've ever done concat, somebody probably told you, drop the index, concat, and then reconstitute the index, kind of like when you do bulk inserts in SQL, and it ended up being significantly faster. Well, don't do apply because you're forced to do that index align concatenation, and that's going to be very slow. So you really, really heavily want to privilege .ag operations, .transform operations, but there are limitations to what you're able to do in those operations simply because they only operate on one column or one row at a time. And so if I wanted to do my weighted price, then the way I could do that is, let's do it like this. I can take my trades and I can add a column to it. And that column is the total volume. And that total volume column will tell me what the total volume is up to that particular point. And no, that won't give me the weighted average price. To get the weighted average price, what I want to do is I want to actually compute the, it's going to be ugly. What I probably want to do is I want to compute the volume times the price for each location, and then perform the summation on that. So I have to do something to kind of set it up. And so usually, decomposing something that needs two columns into one is usually figuring out how can I manually rejoin these into a column so that every operation is just performed on a single column. And so that's not actually that interesting. Let's do the positions, because the position's a little bit easier, and that's where we're going to go for the total volume. What we want to do is we want to figure out what our position was at every point in time. Not what our total position size was at the end of this sequence, but what our position was as of each trade. So if we do something like this, let me grab one of these. And here, let me do an index slice because it's date time and then this. So I'll just slice this to get all the ones on this ticker FECI, whatever that happens to be. Oh, I already have that. Oh, I already did all my imports ahead of time. That's good. There you go. So I want to see, okay, I went from 13,500 plus 49,600. So I went up to 50, 60 something thousand. I want to see what that is ticking up. And that's actually fairly straightforward to do. And then I want to compute where I've actually gone from a long position to a short position. So I can group these and do something like a buy price, average buy price or average sell price. Because what you can think is, if you're computing like an average price of a bunch of different trades, and sometimes they're long positions and sometimes they're short positions, well, it kind of makes a difference. If there's a spread, right, kind of makes a difference which side of that transaction you're on, if you want to look at that average price. And so what you really want is not just the mean price against everything. You want the mean price for all the buys and the mean price for all the sells. So you have to identify what the position is and identify which of these corresponded to a buy and which of these corresponded to a sell. And so what that means is we're going to do the following. We're going to assign a new column into this thing, and it's going to be the total volume. And this is what we were going for before. But when we compute the total volume, what we want to do is we want to make sure that we only look at this one ticker at a time. Because if we look at these, if we don't group up these tickers in some fashion, we're going to get some very weird results where the positions are going to intermingle. And because our indexing is clearly about saying, oh, this is the date, but there's also this partitioning of this data set, what we're going to do is we're going to take this data frame and we're going to group by the ticker. We're going to grab the volume column, and we're going to perform an operation. And the operation that we want to perform here is actually a fairly straightforward one. We could do a cumulative sum, but I want to show you how we could expand this a bit, just so that we can talk about group by. The difference between group by transform and group by ag is group by transform preserves the index, group by ag changes the index. When you group by ag, you're aggregating, so the index is going to be whatever the grouping criteria was. If you group by transform, the operation will be performed on whatever the grouping criteria was, but the index will stay unchanged. This is what I want. I want the original data frame to be exactly how it looked like, except I want one more column on it, and I want that one more column to include my cumulative sum. So I could do this as, a simple cumulative sum like this, or I could do this as a transform, just to show you transform, where I transform each group using an expanding sum. And largely, there's just one of these will be a little bit shorter to write, but they're basically the same idea. And let's just take a look at the first 5 rows of this thing. So here you go. And now I have my total volume. And let's actually look at this just for one particular ticker, just so we can see if that actually worked. And you can see this seems to work. So it's computing what my total volume is. Now that I know what my total volume is, I could compute what the sign of these positions were. So what I could do is I could say, if I take this data frame and I take this total volume column and I ask what the sign of this thing is, I can see is this a long position or a short position. So if it's 1, it's a long position. If it's -1, it's a short position. Not too hard. And once I've done that, I can identify the places where I've gone into a new position, because the places where I've gone into a new position are the places where it's crossed over the 0 axis, where it's gone from being long to short or from nothing to something. And so my new positions are fairly easy to compute on this data frame. I just take that sign column and I group it by ticker, or actually I like to do group by first. So let's do this first on the ticker and then grab that sign column. And then what I can do is I can do a transform on that sign column because I want to keep the same data frame. I'm just creating a new column. So I want to keep the same structure of this data frame. I want the same indexing. I want everything to match up. What I can do is I can look at that sign and I can look at 2 values next to each other and I can sum them. And if you've gone from long to short, that sum should be 0. If you've gone from short to long, from 1 to -1, from -1 to 1, that should be 0. Any place where this is 0, you've actually crossed over the 0 axis and you have a new position. So here, we can now notate all the new positions we have, and we just have to learn how to spell someday. There we go. And so you can see those aren't new positions there, but if we expand this a bit, I wonder if we do enough trades on this thing. Yep, there you go. And you can see this was a new position because we went from a long volume to a short volume. You can see the sign changed. And there, once we know what the long and the short positions are, we can use that in order to figure out what the average buy price and the average sell price are, because it's just an operation on this. And so let's see if we can do let's actually go back and do the weighted price. So we can do that against the average weighted price. As I said, the weighted price here, I want to do this in a group by ag or a group by transform. I don't want to do this in a group by apply just because it's going to be slow. So what I'll do is I'll compute the weighted price first. And that's just a lambda df. And that's just, as I said here, we'll pre-compute the volume times the price. And yeah, so that should give us that. And then our weighted average price is just the sum of those, right? Because and then we have to divide that, don't we? So what we'll do is we'll compute the weights first. That'll make it easier. So we'll compute the weights, and for the weights, what we'll do is we'll take the data frame and we'll group it by each position. Here's where we can actually use the positions. So let's compute the positions so we can figure out what the weighted price is per position. So we're going to back up one more step so we can compute everything correctly. What we want to do is we want to compute what the positions are. And to compute the positions, we're going to do this. We're going to take our data frame and we're going to group it by the ticker. We're going to look at that new column, and we're going to transform it, and we're going to compute the cumulative sum of these, because this will give us what the position is in terms of just a counting up number of, are you position 0, 1, 2, 3, 4, 5, because then we can group by that. If we group by that new, we'll get all the places where it's not a new position, and all the places where it is a new position together, which doesn't make sense. But if we cumulative sum down this thing, then you can see, oh, all of those are position 0 and all of those are position 1. And then we can group these in order to do the operation that we want to do. And we haven't touched the single group by dot apply yet. Once we do that, we can compute our weights by doing the following. We can say group by each ticker and each position number, and grab the volume from that and transform that volume by taking the absolute value of whatever the volume is and dividing it by the sum. So this gives us the corresponding weights. That's how we're going to have to do these weighted sums. Yeah. And once we do that, then we can get the weighted price pretty easily, because what we'll do is we'll just take the volume or the weight times the price. So we'll first pre-compute what the weights are. There we go. So that's our weighted price. And then to do our average price, we've already set this thing up the way we want it to look. So what we'll do is we'll say group this thing by the ticker and the position, grab that weighted price, transform on that weighted price, because I want to preserve the indexing. This is the really key thing, transform versus ag. It's really about, do you want to preserve the indexing or do you want to change the indexing? And there you go. That's your weighted average price per position, your weighted average price on a per position basis. So if you then took this, and if we took this thing and we pivoted into the columns, the value of that sign column, we could actually, let's actually do this down here. If we took this thing and we took the sign column and the weighted price column, right? So here we have all of those. We could pivot that sign column into the columns index. So sorry, pivot this. And what that would give us is what the weighted price was for all the long positions, what the weighted price is for all the short positions. And obviously here, this is giving us on the same indexing, on the same, original indexing of the first, but you can see this is what the weighted price is for each point in time as a rolling average, your average buy price and your average sell price. And obviously what you want to do is you want to do some backfilling or forward filling on this. So, if you do like a B fill type thing, you'll get some backfilling on this just so that you can analyze this later and look at the data and say, okay, at any one point in time, what's my average buy price, what's my average sell price? And so actually I want to forward fill this because this is new information coming in. And so here you can see that's my, my knowledge of what the average price, the average sell price, the average weighted sell price, the average weighted buy price is at every point in time for a particular ticker. And by virtue of how nicely all this index alignment works, this has actually been computed on the entire data frame simultaneously. So now I have trade level data, when I did the trade, on what ticker, how much, and I have the actual rolling weighted average buy price and sell price for all of these. And looking at this, there's one group by missing because these shouldn't match up here and there. So let's just, because the forward fill isn't group by aware. So here I'd have to do a group by forward fill. And because I'm going to preserve the indexing, I want that. And so there you go. And so so here clearly you don't have enough information, on the long side of this. And because I don't like that much, plus, I don't like these not nameable things. This is where I might want to do a rename axis. And We'll say this is what short and long. Axis equals columns. So we can actually see what this thing, we can actually make heads or tails of what this thing actually is. So, ooh, and I actually want to do this. This should be a rename. Just rename axis. This is the one thing that always trips me up. Rename axis, rename, and which one of them changes the values of the axis itself. I thought it was rename axis changes the axis values. I want a set axis. That's what I want to do. This is, the unfortunate thing about the Pandas API. These names are so bizarre. It's so impossible to remember. What's in between rename axis and set axis? As long as you know what you're trying to accomplish, I find that's way more valuable than remembering is it rename axis or set axis. Set axis sets the contents of the axis, and rename axis changes the names of those axes so that you can do index aligned operations, and Pandas can figure out how to line things up. Didn't say I was the expert. I was just saying that maybe if you put a little bit of attention into the index, maybe you could be an expert one day too. I shouldn't say two. Maybe you could be an expert one day and then show me how to remember how to do this without making so many mistakes. But any questions? Any questions? It's a powerful tool. Then you can do some really fancy things that you just can't do in NumPy. And most of that comes down to what? Index alignment. And operating on this is a like index collection of two-dimensional data, or sorry, of one-dimensional data sets. And making sure that your indices are aligned, and in the result, you end up with code which is very dense and requires knowledge of the jargon of Pandas. But for the most part, look, this analysis, very dense and requires knowledge of, all the names of these different arguments. But if I had to do this in pure Python, or if I had to do this in pure NumPy, this would be 100 lines of code, and it would be incomprehensible. It would be so mechanical. I would have no ability to spot check it and say, oh, that's definitely right. Definitely this is dense. But it's dense because it's replacing such an enormous amount of analytical work that I would have to do by hand myself in NumPy, in which case I would basically be reconstituting the index or recapitulating the index. The sad thing about indexing and index alignment in Pandas is if you don't use the index, you're going to end up creating your own worst version of it as a column of your data set, and you're just going to try and do these index aligned operations yourself in the clumsiest, least efficient way possible. Is no one convinced by our? Okay, we have one person who's convinced. Otherwise, thank you all for joining me. If you have any questions, tweet at me, take a look at the video, and see if you can maybe develop a little bit of Pandas expertise by playing around with the idea of the index. Thanks, everybody.